This is lecture 11 for chapter 2 for ODE, and in this lecture I'll discuss the case of equal eigenvalues, and this will give us the ray or the single tangent phase portrait. In the previous lecture we looked at the case of two distinct real eigenvalues, and that gave us the saddle, source, and sink phase portraits. Here we're looking at you can say one eigenvalue or identical eigenvalues. Now whether we get the ray pattern or the single tangent pattern depends on the eigenvectors. And finding the eigenvectors is a little different, well, quite a bit different in this case compared to the previous case. So we're going to do the canonical examples first, that is examples with very simple coefficient matrices and very simple patterns with the eigenvectors usually lined up right along the coordinate axis. So here's our case of a diagonal matrix with equal values along the diagonal. If you remember from the previous lecture that for the diagonal matrix the eigenvalues are the values on the diagonal. So that means we have two eigenvalues and they happen to be both equal to lambda 1. Okay. Now for the second case, this will be the single tangent pattern. We'll have a similar simple coefficient matrix A, but this will be triangular. And for the triangular matrix, the eigenvalues are also on the diagonal, but there's a term that's off the diagonal. In this case I'm calling it alpha and saying that alpha is not equal to 0. So again we have the eigenvalue there's one eigenvalue and or you could say two equal eigenvalues. So we'll do the ray pattern first, and the ray pattern again, here is the coefficient matrix, and I'm leaving the subscript 1 on the eigenvalue to remind us that there is only one of them. You don't need it, you could just write lambda. Okay, so here we have this diagonal matrix and we need to find the eigenvector. The eigenvector is a solution of this equation, a minus lambda I times v1 equals 0. So if I'm subtracting, so our eigenvalue is lambda 1, so if I subtract it here and I subtract it here, all I get for this is a bunch of zeros. These are the coefficients of the vector v, and they have to equal 0. Well, you could put anything you want for vx1 and vy1, and you would still solve this, you'd still have 0 as a result. So we can have any eigenvector, and because we can have any eigenvector, we'll pick a simple one, and that's 1, 0, which is the same as the x-axis, so to speak. Okay, and now we repeat the process. Now we go back and repeat the process, and of course we're having things are going to look pretty similar. So a minus lambda, well, I just used lambda 1 here because we only have one eigenvalue, and now we're looking for components of v2 if we can find them, and of course we can. So a minus lambda 1 again is like nothing, and we would have vx2, vy2, the components of v2, and that has to equal 0. Again, any eigenvector will do. So we will pick one that is linearly independent from the first eigenvector. So v1, we picked 1, 0. The obvious choice for v2 is 0, 1. So for this diagonal matrix with equal values on the diagonal, by that we mean A has the same values along the diagonal, we can find two linearly independent eigenvectors, and they happen to be the x-axis and the y-axis. Okay, and then the solution is the linear combination of the two solutions. The first solution is and I could have left a y here, 1 here. Say we put 1 here just to remind us, times v1 plus e to the, again, lambda 1 because it's the same, times v2. Whoops, I'm sorry. That's your first solution. Your second solution is, and then it's the second eigenvector. Then the general solution is a linear combination of them. That's where we have the C1 and C2, of course, as usual. So now, when we go to draw the phase portrait, the eigenvectors are along the coordinate axis. We know that. But what are the remaining solutions? Previously, when we had the source and the sink pattern, we had eigenvectors lined up. Say we had a source. Then the solutions that were in between, so to speak, kind of had a U shape to them, sort of. And they filled in like this. For this ray pattern, we're not going to have that. Instead, we're going to have straight lines everywhere going through the origin. To see that these are straight lines, let's look again at the solution. So we had y of t was x of t, y of t, and this became c1 e to the lambda t. I just go like that. So writing out the x and the y, we can see that x of t c1, interesting, e to the lambda t, right, because you have a 0 elsewhere, and then y of t is c2 e to the lambda t. Okay, so I erased my solutions, but I have an error here, so let me write that back again. X of t is c1 e to the lambda t, y of t becomes c2 e to the lambda t, and I got that from the general solution that we had on the previous slide. I'll go back to the previous slide right now. So here is the x of t on the, the first entry in the vector, so that would be e to the lambda t c1 times 1, but there's no c2 component because that's multiplied by 0. And now we can look through for the y of t. We're not going to have this first component at all. We'll have e to the lambda t, and we'll have the c2. Okay. Okay, so if we look at the ratio of these two, so I put y of t over x of t, I should have had e to the lambda t times c2 over e to the lambda t times c1, c2 over c1. The idea is the same. It's going to be a constant. Okay, sorry I made this mistake. I could go back and redo all the slides and the lecture, and then you could have everything perfect, and it would be like a robot lecture. It'd be boring. On the other hand, you can watch this, watch me have errors, which might be painful. So take your pick, boring versus painful. I think most people would pick painful over boring. I don't know if that's a wise choice. So here's our ray pattern, and you can see why it's called ray. It's also called starburst. I know there are other names for it, but I use ray. Okay, we have here and here in bold the eigenvectors, and we were able, because of the form of the matrix, to find two linearly independent eigenvectors. These happen to be lined up nicely with the coordinate axis because we're doing the canonical examples. And then you see the other solutions, instead of doing something like this, they are straight lines right through the origin, giving this pattern. Now we'll look at the case of the single tangent. And in the single tangent pattern, we cannot find another linearly independent eigenvector. And this occurs also when you have the case of two identical eigenvectors, but you just can't find the second two identical eigenvalues and you just can't find the second eigenvector. So the canonical example again is a triangular matrix, so I'll write that again here. So A was, we had some entries here, and we had an off-diagonal entry that was non-zero. So when we work through the equation here, this is lambda 1 doesn't matter because we only have one of them, times vi, looking for the eigenvector. We won't have all those zeros like we had before. That's how we got the second identical second eigenvector. Instead we have this off-diagonal matrix, off-diagonal entry here, and that's going to limit us. So I'm going to write this out. So it'd be 0 in component form, 0 vx1 plus alpha vy1 equals 0, or this one, which doesn't give us much information. But from here we see any vx1 will do, and when anything will do we give it a 1. But this next entry has to be 0. The vy1 has to be 0. So here's our first eigenvector. But if we repeat the process, we'll get exactly the same thing, right? Because the second eigenvalue is the same as the first one, so this matrix will be the same. The only thing different will be that we'll be looking for the components of V2. But we'll have the same equations and we'll have the same limitation. We could pick another V2, but if we pick another V2, for example, we could say okay, we know Vy2 has to be 0 by this equation, okay, because we have the same equation. Vx1 could be anything. Well, so if I pick 2, what have I got? I have a multiple of Vy1, so they are not linearly independent. And the eigenvectors must be linearly independent, so in this case we cannot find another eigenvector. But we need one. Well, actually, we could use another eigenvector, but what we really need is another linearly independent solution, because, okay, so the whole goal is to find the basis for the solution space. And right now, with one eigenvector, we found one solution. Okay, and now we need to find another one that is linearly independent from y1. We can't do it through the eigenvectors, so we'll have to do it a different way. So we look at the idea of the method of undetermined coefficients and get an idea from there. And if you recall, when you had a solution that was e to the lambda t, say, and you wanted to find the solution for the forcing function, and your forcing function was also e to the lambda t, then you assumed that you had a solution of the form t e to the lambda t. You multiplied it by t. You might remember that. Okay, so we're going to take this and multiply it by t, and that will give us part of the second solution. We're going to add to that, and we have to add to that another vector u with the same time dependence. We need that u because this y2 has to solve the system. There are conditions on u. U will not be an eigenvector. It will just be another vector that's added into that second solution. So we'll derive those conditions on u. So we have the system here as before, and we want to, we should put C1s and C2s here. There should be a C1 here and a C2 here. Okay, so we want the solution. The solution is going to be a linear combination of y1 and y2. So here was the y1 that we found from the eigenvector the usual way. And here was the assumed solution that we have for y2. So we're going to set, this has a lot of pain in it, doesn't it? So set y1 and y2 both equal to 1. For simplicity, and we're going to take the derivative. What we have to do is put this back into the equation. So we take the derivative, and of course I'm leaving the ones in here just to remind us that we only have one eigenvalue. So here's the derivative of the first term. The second term has that t in it, so we end up with some extra terms here, and then it also has the u. So that will give us the left-hand side. For the right-hand side, we have to multiply this by a. So I'm going to multiply this. I'll multiply all of this by a with C1 and C2 equal to each other. Now I'm going to put them into that equation, into this matrix equation here, and there's going to be e to the lambda 1 multiplying every single term, and we can cancel that. So here's what we get, and this is the result of and you'll notice there's some terms that have t's in them. Here's one, and here's another one, and there's some terms that don't have t's. So we're going to equate these similar terms, and that will give us two equations. Here's the first one, equating the ones that have t's in them. Here's the one equating the ones that do not have t's in them, because these are equal. Then if we rearrange this, look what we get for that first one. That is a condition on the eigenvector, right? That means V1 is an eigenvector. And that's how we found V1, so we know this equation is true. We look down here, we'll see the same thing right here, and then we have a term with u in it and equal to V1. That's from rearranging this. Okay, we know this is 0, so we can set this equal to 0 right now, and all we end up with is that. And that is a condition on the vector u. So we use that to find the components of the vector u. We're going to finish the canonical example here. Here was the equation. We know that A minus lambda, okay, recall that A was that upper triangular matrix. This also works for lower triangular, not a big deal. So we had, okay, and we want to find components for u, so we'll write the components of u as u in the x direction, u in the y direction. Here's the two components of u. We know that V1, and that was a V1 we found earlier. So we can write this out, and we can solve for these two components. Obviously, the x can be anything. It's going to be 0, so who cares what that is? I'm going to put that to 0 because it can be anything, but in this case we want a 0 because we're equal to 1 over here. Now, uy is just 1 over alpha. Like I say here, for a lower triangular matrix, you end up with something similar here. Okay? Now this is called a single tangent system because the other solutions are not going to be raised anymore. They're going to have more of that U-shape that we saw in the source and sink and saddle phase portraits. But there's only one eigenvector, and they all converge to that asymptotically either in forward time or in backward time. That's why it's called a single tangent pattern. Now that single tangent is, they're making a tangent along the eigenvector, but the eigenvector is a solution, so it's, if you put C2 equal to 0, you'll be moving along the eigenvector. That, by uniqueness, that will separate out solutions below it and above it, since no solution can cross it. And here are just two examples. Let's say that your eigenvector is 1, 0, and you have an eigenvalue of -1. All right. Then here's the eigenvector right here, and you see the other solutions coming in towards, there's only one equilibrium point here. They're all coming in, approaching asymptotically to that equilibrium point, but they come in along the eigenvector V1. Or if it starts here, solution starts here, it's going to come up here, and again approaching V1 because it's a sink. All right, it's approaching the equilibrium. If that eigenvalue was positive, say it was +1, then these arrows would be reversed and the solutions would be moving out here, but they would approach that single tangent in backward time. This is just another example where the eigenvector is chosen to be, eigenvector ends up being 0 and 1 along the y-axis. Now I want to work through a non-canonical example, so we'll use something from the textbook on page 321. There was a critically damped harmonic oscillator given with these values. Okay. Now these are, the single tangent is the example of a critically damped harmonic oscillator. Okay. So I'm going to take this and I'm going to write it as a system. So the coefficient matrix is going to be 0, 1, -2, and -2 root 2. This is not an upper triangular matrix or lower triangular matrix. I'm going to have to solve for the eigenvalues. So the trace of that matrix is here, -2 root 2. The determinant is 2. And since t squared equals 4d, that's why we have that, if you remember from the quadratic formula, when t squared equals 4d, the determinant, the term under the square root sign, the quadratic formula is 0. Okay, so we're left with one eigenvalue, and here's a characteristic polynomial. Remember, characteristic polynomial is lambda squared minus, remember, minus times a trace plus the determinant, and that has to equal 0. So substituting some values and then solving it, you can listing factors, or you can use the quadratic formula. Either way, you find out that there is only one eigenvalue, and it is minus root 2. Now we can go look for the eigenvector. So this is the equation. Equals 0. Okay. Substituting for a minus the eigenvalue that we found in the previous page, we end up with these equations. All right. So I write them out in component form here. So by solving these equations, these are not a system of equations, remember, because this matrix, the determinant of this matrix is 0. They're multiples of each other, these two lines. Okay, but you can kind of look through here and find out that one choice for the eigenvector, that v1, is, put a 1 here, and if I put minus the square root of 2 here, then, okay, vx1 is 1, and this is negative square root of 2, I will get 0. Of course, that works in the second equation as well. So here's my v1. So the solution is going to be y1 plus y2. y1 is some multiple of this, which is the eigenvalue times v1, here's v1, plus c2 times, we have a t now, times the eigenvalue times v1, e to the lambda t times v1, plus e to the lambda t times u, and u has to satisfy this equation. So I'm going to substitute that into here. Again, we have a minus lambda 1I, which is the same as before, the components of u, and here's the v1. Now we can write this out in component form, of course. Square root of 2 times ux plus u1. It has to equal 1 times uy has to equal 1. Alright, so here's one choice. Let's let ux be 0 and ui be 1, and that satisfies these equations. So that's a simple vector u. We always go for the simplest ones. So now we have the eigenvalue, we have one eigenvector v1, and we have u, and we have the form of the solution. So here's the solution. So this is c2y2, and this is c1, and this would be e to the lambda, the repeated eigenvalue, times t times v1, and this is c2 times t e to the lambda t times v1 plus, e to the lambda t times u. So here's the u, here's the v1, Here's the V1, and you see that same time dependence throughout, but you need a T right here. If this is a harmonic oscillator, say it's mechanical, then the x of t is displacement, so this would be displacement, and then the derivative is velocity. So here are the solutions. Now for the phase portrait, this is non-canonical. We don't expect that the eigenvector is lined up with the coordinate axis, and it's not. Here's the eigenvector, and you see all the solutions are approaching it. This is a sink. Here's the one trivial equilibrium solution at the origin, and all the solutions are approaching in forward time along the tangent to this eigenvector. So that was a non-canonical single tangent system. So for review, when you have only one, or rather you have repeated eigenvalues, you have two possible phase portrait patterns. One's the ray, and the ray you can find two eigenvectors, and all solutions are lines. They're all lines going through the origin. If you can't, you can only find one eigenvector, then you can find an additional vector u, which is not an eigenvector, and the form of solution we discussed here. In this case, you have the single tangent pattern.